Hello all, I am Dr. Aysha Zeneeb Majeed, Associate Professor, Department of Civil Engineering, Rajagiri School of Engineering and Technology. This is the fourth lecture on Module 3 of Engineering Mechanics. This lecture deals with the force systems in space. Now, in order to solve the force system in space, it is better to use the vector approach, which is simple when compared to the scalar approach. So let us first consider a force in space. For that I am considering a cuboid, and let x, y and z directions be shown by the edges, these edges of the cuboid of origin O, and let OA be a diagonal. What is the if the cuboid or this is a parallelepiped basically. Now if the let us say that it is a cuboid, okay, it's having all the sides uniform as A. In that case, of uniform length L. In that case, A will be having an coordinate x, y, z as L, L, L. Okay, and O will be having coordinates as 0, 0, 0. Yeah. So let F be the force vector which is acting along OA. Okay, and having a magnitude of F. Then we can resolve this force vector into three components. Three mutually perpendicular components, one along the x direction fx, another along the y direction fy, and the third along the yz direction having a magnitude of fz. Let lambda be the unit vector along the line of action of the force F or along OA. So you can represent the force in vector form as F with an arrow on top showing that this is a force vector is equal to F, which represents the magnitude of the force into lambda with a cap on top, which is the standard representation of unit vector. So lambda with a cap is a unit vector, and in this case it coincides with the direction of the force or line OA, and unit vector always has a magnitude of unity. Now if you consider x, y and z axis, then we have unit vectors represented as I, j and k along the x, y and z directions respectively. And theta x, let theta x be the angle that the force F makes with the horizontal component. Theta y be the angle the force F makes with the line of action of the force F makes with the y axis or the vertical component. And theta z be the angle the force F makes with its z component. Then let these be the angles. So now we can write Fx, the horizontal component of the force, as F into cos theta x, right? F is the magnitude of the resultant force. Now Fy you can write as F cos theta y, and Fz you can write as F cos theta z. Now if you have got all the three components, and if you know that I, j and k are the unit vectors along these components, along these x, y and z directions, then you can write the vector force F as Fxi plus Fyj plus Fzk, right? This is how you represent the force in vector form. Now what is Fx? Fx is F cos theta x, so you can write it as F cos theta xi plus F cos theta yj plus F cos theta zk, where F you can take outside, so it becomes F into cos theta xi plus cos theta yj plus cos theta zk, or you can write F is equal to F into lambda, because you know that basically F is written as F into lambda. So what is lambda from these two equations? You can write lambda is equal to cos theta I plus cos theta yj plus cos theta zk. Now this cos theta x, cos theta y and cos theta z are called the direction cosines. And how will you get direction cosines? Cos theta x can be got as Fx by F, right? You go to the previous equation, the first equation. Cos theta x is Fx by F, cos theta y is Fy by F, and cos theta z is Fy by F. Just understand that I have not put any arrow on top. So these are all magnitudes. Fx, Fy, Fz and F. These are all magnitudes. When I put an arrow only, it becomes a vector. Okay. So now these direction cosines are not independent of each other. They follow the condition cos square theta x plus cos square theta y plus cos square theta z is equal to 1. And how will you get the magnitude of the force vector f, which is given by f is equal to square root of fx square plus fy square plus fz square. Now let us come to the term position vector. Position vector is a vector that locates a point in space relative to another point. So let us consider again a reference axis xyz and a parallelepiped. Let AB be the diagonal and let the force F be acting along the diagonal. Just understand that the force F is not from A to B, but its line of action is coinciding with the diagonal AB. That is all. Let x1, y1 and z1 be the coordinates of A and x2, y2, z2 be the coordinates of B. Let lambda AB be the unit vector along AB. Now what is dx? The distance along the x direction of the parallelepiped. It is nothing but x2 minus x1. Similarly, dz will be z2 minus z1 and dy will be y2 minus y1. Now the position vector RAB is defined as the vector that locates a point in the space, right? So that is dxi plus dyj plus dzk. That is the position vector of AB. That is from A to B. Okay. So from when it is from A to B, it is written as x2 minus x1 into I. Make it a point that it is not x1 minus x2, it is from x2 to x1. So when it is RAB, it is from B to A, B minus A. That is x2 minus x1. Okay. So RAB is x2 minus x1 into I plus y2 minus y1 into j plus z2 minus z1 into k. Now RAB can again be written as magnitude of RAB into unit vector along AB. So what is unit vector along AB? RAB divided by magnitude of AB. So what did I get as RAB? RAB is nothing but the vector AB, right? So from the vector AB, I got the unit vector along AB, which is vector RAB divided by magnitude of RAB. I can write as 1 by RAB into dxi plus dyj plus dzk. Now what do I know? F is equal to, vector F is equal to magnitude of F into unit vector lambda, right? So that is F into what is lambda? Lambda is, I have written RAB, magnitude of RAB as D. Okay, the length of the line AB as D. So 1 by D into dxi plus dyj plus dzk. So what is Fx? Fx will be F into dx by d. Fy will be F into dy by d. And Fz will be equal to F into dz divided by d. Okay, so to represent the vector in represent the force as a vector, there are mainly three steps involved. One is to determine the position vector RAB along the 2 points on that line. What it means is that if you are having, if it is told that the force is the line of action of the force passes through points A and B, then you can always determine the position vector at of AB. Once you get the position vector, you can get the unit vector. Unit vector is nothing but the position vector divided by the magnitude of the position vector, and you multiply the unit vector with the magnitude of the force to get the force vector. Okay, now if you are given two vectors, say A and B, where A is equal to AXI plus AYJ plus AZK and B is equal to BXI plus BYJ plus BZK, you know how to add the two vectors, right? How will you add the two vectors? You add the I terms together, j terms together and k terms together. So it becomes ax plus bx into I plus ay plus by into j plus az plus bz into k. Similarly, how will you subtract two vectors one from the other? Subtract the corresponding components, right? The ax minus bx into I plus ay minus by into j plus az minus bz into k. Similarly, how will you get the resultant of n forces acting on a body? You represent each force as a vector and just add up those forces. That means add the I component, j component and z component separately. We will be getting the resultant of that force. So it's simple when it comes to vectors in space. And what about the equilibrium of forces acting on the body? You say that you add up all the forces. If sum of all the forces is equal to 0, then you say that the body is in equilibrium, or the net force acting on the body is 0. So let us do one problem. Determine the magnitude and magnitude of the resultant and its direction cosines for the following system of non-concurrent coplanar non-coplanar concurrent forces. 300 kilonewton with a coordinate plus 3 minus 4 plus 6, 400 kilonewton plus 2 plus 4 plus minus 5 as the coordinates, and 200 kilonewton minus 4 plus 5 and minus 3. Now please note that these are the end coordinates of the forces. I mean, one of the point through which the force is acting, and since it is concurrent, we can assume that meeting point as the origin O. Okay, so it is concurrent forces, we are considering the meeting point as the origin, and these are the forces, three forces acting in three different directions. Okay, fine. So what it says is that the force F1, if you extend the line of action, it will pass through the point 3 minus 4 6, and likewise. So first is to determine the position vector. How will you determine the position vector? Position vector of 1 will be, it starts from origin and it ends at the point 3 minus 4 6. So x2 minus x1 means 3 is x2 and x1 will be 0. Similarly, minus 4 is y2 and y1 will be 0, and 6 is your z2 and z1 will be 0. So you will be getting it as 3 minus 0 into I plus minus 4 minus 0 into j plus 6 minus 0 into k, or it is 3i minus 4j plus 6k. Similarly, you can find out R2 and R3. So you got the position vectors. Now what's the next step? To determine the unit vectors. How will you determine the unit vector? Lambda 1 is equal to position vector R1 divided by magnitude of position vector R1. How will you get the magnitude of position vector? Square root of the coefficients, sum of the squares of the coefficients. That is square root of 3 square plus minus 4 square plus 6 square will be magnitude of R1, and position vector will be 3i minus 4j plus 6k. So what is lambda 1? 3i divided by square root of 3 square plus minus 4 square plus 6 square. You will get it as 0.384. Similarly, the j component and the k component. Likewise, you can determine the unit vector lambda 2 and unit vector lambda 3. Once you have determined the unit vector, how will you get the force vector? Force vector is equal to unit vector multiplied by the magnitude of the force. So F1 will be equal to 300 multiplied by lambda 1. F2 is equal to 400 multiplied by lambda 2, and F3 is equal to 400. F3 is equal to 200 multiplied by lambda 3. The next step, next part of the question is to determine the we have not completed the first part itself, to determine the magnitude of the resultant. So we have got F1, F2 and F3. These are the components, right? So we need to find out the resultant of these three components. How will you get that? To determine the resultant force, you just have to add up all the three forces, like F1 plus F2 plus F3, but it is vector addition, right? How will you add the three vectors? You add all the I components, right? So 115.2 minus 119.2 minus 113.2 will give you minus 117.2 I. Similarly, you add up all the j components, you will be getting 226.2, and when you add all the k components, you will be getting 152.8. So that gives you the resultant force vector. Now what is the magnitude of that force vector? That is a question. Magnitude of the resultant. How will you get the magnitude? Square root of the coefficients of I, j and k, the square of that, right? Sum of the squares of the I, j, k coefficients, and take the square root of that. So square root of minus 117.2 square plus 226.2 square plus minus 152.8 square, which will be getting as 296.98, which is the magnitude of the resultant. Now the next part is to determine the direction cosines. What is the expression for determining the direction cosine? Cos theta x is equal to fx by f. I have told you before also, fx and f are the magnitudes. Okay, these are not vectors. So what is fx? It is minus 117.2 divided by the magnitude of f is 296.98. You will get it as minus 0.394 is cos theta x, which is the direction cosine. Similarly, you can find out cos theta y and cos theta z. Let us do one problem. Another problem. A force vector is represented by a line AB. The coordinates of the point A is 2, 4, 3 and B is 1, minus 5, 2. If the magnitude of the force is 10 newtons, find the component of the force along the x, y and z axis and angle the force makes with the x, y and z axis. So the first question, the first part is given as the force vector is along the line AB. Okay, so that means the coordinates A and B will give you the position vector, and once you get the unit vector from the position vector, you can determine the force vector by multiplying the unit vector with the magnitude of the force vector. Right, so first let us determine the position vector. Position vector AB will be x2 minus x1I plus y2 minus y1j plus z2 minus z1k. Here x1, y1 and z1 is 2, 4, 3, and x2, y2, z2 is 1, minus 5, 2. So it is not RBA. If it is RBA, it will be x1 minus x2. If it is RAB, it is x2 minus x1, right? So from B to A. So it will be x2 minus x1, that is 1 minus 2 into I. Similarly, minus 4, minus 5 minus 4 into j, and 2 minus 3 into k. So you get the position vector as minus I minus 9j minus k. Now once you have got the position vector, you determine the unit vector by dividing the position vector by its magnitude. So you will get it as minus 0.1097 I minus 0.98 j minus 0.1097 k. Then you can determine the force vector. Just multiply with the magnitude of the force vector, which is 10. So this is the force vector. And so what are the components? Fx will be the component I component, right? So that is minus 1.097. Fy is minus 9.8 and Fz is minus 1.097. So what's the direction cosines? Direction cosine cos theta x is fx by f, which is minus 1.097 by 10. So theta x will be equal to 96.29. Similarly, theta y you will get as 168.52 and theta z as 96.29. Let's take another problem to determine the magnitude of the resultant and its direction cosines for the following system. So here you can see there is a pole with the base taken as the origin 0, 0, 0, and the other end is A along the Z direction. The height of the pole is 6 meters. So 6 meters is along the Z direction. So if I try to write the coordinates of A, the coordinate of A will be 0, 0, 6. Okay. So I am considering the base of the pole as the origin, and I am trying to come with the coordinates of the points A, B and C. So you can see there are two forces, FC and FB. FC is along the line along the rope AC, and FB is along the rope AB. So once you get the coordinates of B, C and A, you can calculate the position vectors of AB and AC, from where you can calculate the force vectors. So first thing is to try to get the coordinates of A. So as I said, the coordinate of A will be 0, 0, 6. Coordinate of B, if you take, B is along the xy plane, okay, and along the positive x direction it is going by a distance of 3. So x is 3. Along the y direction, positive y direction, is going by a distance of 2. So y is 2, and since it is in the xy plane, z coordinate is 0. And similarly for C, along the positive x direction it takes a distance of 2 meters, right, and along the my negative y direction it goes by 3 meters, and since it is in the xy plane, z component is 0. Now we can determine the position vectors. So what is RAB? RAB will be the coordinates of B minus the coordinates of A, right? So 3 minus 0 into I plus 2 minus 0 into j plus 0 minus 6 into k, which is 3i plus 2j minus 6k. Similarly, what will be RAC? 2i minus 3j minus 6k. So now you can determine the unit vectors lambda AB and lambda AC. It is directly RAB divided by magnitude of RAB. Similarly, RAC divided by magnitude of RAC. Once you have determined, you can determine the force vectors FAB and FAC as FAB into lambda AB. Magnitude of FAB is 840 kilonewton. So multiplied by the unit vector along AB. Similarly, 420 kilonewton is FC. So multiplied by the corresponding unit vector. So you got the force vectors. So now we can determine the resultant force. What is resultant force? It's nothing but FAB plus FAC. So that is vector FAB plus vector FAC, which is equal to 479.32 I plus 60.48 J minus 1079.8 K. And how will you get the magnitude? Square root of the square sum of the squares of the components. We will get it as 1182.9 kilonewtons. Now you can determine the cosine direction cosines as well. It is fx by f, so 479.32 divided by 1182.9 is minus 0.405. Similarly, cos theta y you will get as 0.051 and cos theta z you will get as minus 0.912. Let us see some of the properties of vectors. One is the dot product of vector. Dot product means if you have two vectors, if you do the dot product of two vectors in the same direction, you will get the magnitude. So that is I dot I is equal to 1, j dot j is equal to 1 and k dot k is equal to 1. Whereas if you do the dot product of two vectors which are mutually perpendicular, it will be 0. That is one component of one vector on with respect in the direction of the or perpendicular to it is 0, right? So I dot j is equal to I dot k is equal to j dot k is equal to k dot j is equal to k dot I equal to j dot I equal to 0. So this is I and this is A and B. So what is the application? If you do the dot product of A and B, you will be getting the product of the components along the directions and sum of the products of the mutually perpendicular components. So that is ax bx plus ay bay plus az bz, and also a dot b is equal to ab cos theta. That is a magnitude of one vector into magnitude of the component of the magnitude of other vector in the direction of the first vector. Similarly, cross product is I cross I equal to 0. That is the cross product of two vectors in the same direction is 0, whereas the cross product of two vectors mutually perpendicular to each other will be 1. Now there is one sign that you have got to follow, that it will be positive if it is in the clockwise direction. The cross product is taken in the clockwise direction, that is I cross j, sorry, anti-clockwise direction. I cross j, I to j it is anti-clockwise, so it is 1. J cross k is 1 and k cross I is 1, whereas I cross k, it is in the clockwise direction, it is minus 1. K cross j is minus 1 and j cross I is minus 1. So you can find out the applications are there many where to determine many components. We will see that. So basically a cross b is nothing but the determinant of the matrix ijk ax ay az and bx by bz. Now a cross b is equal to ab sin theta. Now how to get the moment of a force about a point A? Moment of the force about point O is given by the cross product of the position vector multiplied by the corresponding force. Now this position vector is directed from the origin to any point on the line of action of the force. Okay, so let us say you are having a reference axis and you are having this AB with x1 A as x1 y1 z1 and B as x2 y2 z2, and let F be the force which is directed along AB. Okay, so what do you mean by the position vector? Position vector is directed from the origin. Okay, it has to be directed from the origin and then to any point on the line of action of the force. So R can be a position vector. The other green in this can also be a position vector, because we can have the position vector to any point onto the line of action of the force. Okay, so only thing is that we should know that point, then only we can find out the position vector. So you can write R cross F as I j k Rx Ry Rz. I have written it as Rx Ry Rz because it can be either x1 y1 z1 or x2 y2 z2. Anyone will be, you will be getting the same answer. And then R cross F, right? So components of F, that is Fx, Fy, Fz, or you can write it as Rf sin theta. So let us consider the moment of the if the case 1 wherein there is a pipe which has been trying to, one person is trying to rotate that pipe. The lever arm is D and F is the force that is acting. F is perpendicular to this pipe, right? The distance is the perpendicular distance is d. So we know F is m is equal to r cross f, or you can write it as r f sine alpha, or f into r sine alpha. Now in this case it is directly you take the second case, it will be much more clear, this case B. So there you can see that the position vector r is up to the point f, and f is at some angle alpha. Okay, so now you see this, if that angle is alpha, the inner angle is also marked in yellow, is also alpha, and you can write sine alpha as d by r, or what is r, what is d? D is equal to r sine alpha. So it is nothing but f into d, and what is d? D is the perpendicular distance, right? So it is basically nothing but force multiplied by the perpendicular distance, whatever we did in the scalar approach, again the same thing. And now see the way the moment is getting, the moment is in the direction which is anti-clockwise with respect to the axis of the pipe, which is OO, right? So you say take your right hand thumb rule, and you see that the four fingers, it shows the direction of the moment, and the thumb will show the direction of the moment vector. So if it is an anti-clockwise moment, the moment vector is acting up. Okay, that's the direction of the vector. So that is how we can find out the moment of the force about a point O. Let us do one problem. Calculate the moment of a force about the base point O of the 600 Newton force shown in the figure. So the solution, you know, moment about any point O is equal to r cross f. So here f is having a magnitude of 600 newtons. Now we need to find out the force vector as well as the position vector. Okay, so how will you determine the position vector? Position vector is x2 minus x1. So it is from the origin to any point on the line of action of the force. So one line of action of the force meets at the point A. So if you know the value coordinates of A, you can determine the position vector. How will you determine the point to A? With respect to O, it is along the positive y direction 4. So that is y is 4, and along the positive x direction it is 2. So 2 comma 4 comma 0, because there is a z direction, there is no component. It is a planar case, right? So what is your r? R is equal to 2y plus 4j. Now you determine the position vector. Now here the angle is given 40 degrees. So how will you determine the position vector? Along the x direction, what is the component? 600 cos 40. So 600 cos 40 I, and along the y direction it is minus 600 sin 40. So minus 600 sin 40 j. So you'll get it as 459.6 I minus 385.7 j. So what is r cross f? ijk, rx, ry, rz, and fx, fy, fz. Get the determinant, and then you will be getting it as minus 2610 kilonewton meters. So what is the negative sign? Negative sign indicates the moment is acting in the negative z direction. That's it. It is a clockwise moment. So it is acting in the negative z direction.